This lecture will explain about flow around a circular cylinder. This is a continuation from superposition of basic plane potential flow. For this time, the combination is from uniform flow with doublet. Before we proceed to that combination, let's recall what is actually the potential flow. Before that, let's watch this video. So flow fields for which an incompressible fluid is assumed to be frictionless and the motion to be irrotational are commonly referred as potential flow. Potential flow can be simulated by a slowly moving viscous flow between closely spaced parallel plates, as you can see in this video. For such a system, dye injected upstream reveals an approximate potential flow pattern around a streamline airfoil shape. Similarly, the potential flow pattern around a block body is shown, as can be seen in this video. This is a block body. Even at the rear of the block body, the streamline closely follow the body shape. However, this simulation is not a real simulation where flow separation at the rear body is not captured in this potential flow simulation. Okay, so for this last combination, as was noted in the Rankine oval section, when the distance between source sink pair approach 0, the shape of the Rankine oval becomes more blunt and in fact approach a circular shape. Okay, so just recall in previous previous lecture for the Rankine oval, we have a distance, separated distance between the origin to the source and sink, which is defined as A. When this distance is approaching 0 for the source and sink, the Rankine shape will change to the circular shape. So that's why for this combination, a doublet combined with a uniform flow can be used to represent a flow around a circular cylinder. As usual, we can define the stream function psi and also velocity potential phi. So as you can see in this slide, for the psi, it is equal to ur sine theta minus k sine theta over r. Okay, where ur sine theta is stream function for uniform flow, which is uy, and then negative k sine theta over r is doublet for stream function for doublet. And then for the velocity potential, it is equal to ur cos theta plus with k cos theta over r. In order for the stream function to represent flow around a circular cylinder, it is necessary that psi equal to constant for r equal to a. Okay, so as you can see in this figure, the radius is defined as a, and then around this closed body, it is psi equal to 0. Hence, the stream function can be rewritten as psi equal to u minus k over r square r sine theta. So rearrange the first equation for the psi, and then we get this kind of equation. By setting the psi equal to 0, where r equal to a, r equal to radius, which is defined as a, we can come up with this equation, which is u minus k over r square equal to 0, or we can define k, which is the strength of this doublet, equal to ur square or ua square, because now r equal to a. Okay, so let's watch another video for the velocity potential over a circular shape. Okay, so the streamline for potential Flow past an object can be approximated experimentally by use of device called a helical cell. The cell consists of two very closely spaced parallel plates. Okay, so you have spaced parallel plate with the two-dimensional object of interest sandwiched between the plate. So this cylinder is placed between these two plates, top and bottom plate. The streamline are made visible by the injection of dye. It can be shown that the streamline for this type of flow are the same as those potential flow past the object. So potential flow streamline for flow past a circular cylinder are approximated here by using a thin circular model in a cell. Okay, so a similar streamline pattern could be obtained if the model was removed and a closely spaced equal strength source or sink pair was carefully inserted into the uniform flow. Note that the flow is symmetrical both top and bottom and front and back. Okay, so we can rearrange the stream function and velocity potential, which is psi equal to u r 1 minus a square, because now k equal to u a square, as mentioned in the previous slide, a square over r square sine theta. Y for the phi, which is velocity potential, it is equal to u r 1 minus a square over r square cos theta. The velocity component can be obtained from stream function of velocity potential equation, which is radial velocity and also tangential velocity, which is Vr, radial velocity, d psi over d phi over dr, or also equal to 1 over r d psi over d theta, and then differentiate psi or velocity potential with respect to r or with respect to theta. We obtain u1 plus a square over r square cos theta, and then the same goes for the tangential velocity. Differentiate with respect to r if for the psi, and then with respect to the theta if for the velocity potential, and then the final equation we obtain a minus u 1 plus a square over r square sine theta. Okay, so on the surface of the cylinder where r equal to a, the radial velocity is equal to 0. Okay, so no radial velocity at the closed surface at the solid body, and then tangential velocity, we tangential s surface equal to negative 2u sine theta. Okay, so we this equation is obtained by substituting substitute the a equal to r equal to a, and then you will obtain negative 2u sine theta. We observe from this result for the tangential velocity at the surface that the maximum velocity occurs at the top, okay, at the top and bottom, where the sine equal to 1, which is sine at plus minus pi over 2, and has magnitude of twice the upstream velocity u. Okay, so at the top and bottom of this sphere, of this cylinder, the maximum velocity can be obtained, where this maximum velocity basically double the upstream velocity, which is uniform velocity u. Okay, so we can determine velocity, and then now since it is irrotational, incompressible, and then steady state, so we can define the pressure at any point within this combination based on the Bernoulli equation. Okay, so based on Bernoulli equation, PO plus half rho u square, limit pressure, equal to PS, the surface pressure, plus half rho v tangent theta s square. Okay, v theta s basically the tangential velocity, that we obtained from previous slide. Okay, so substitute the v tangent v theta s equal to -2 u sin theta, we obtain this ps equal to p naught plus half rho u squared 1 minus 4 sine squared theta. Okay, so this graph basically comparison between theoretical, so this is the theoretical symmetrical pressure distribution expressed in dimensionless form of typical measured distribution. Okay, so this figure clearly reveals that only on the upstream part of the cylinder is there approximate agreement between the potential flow and the experimental result. Okay, so as you can see, the dashed line is the experimental result, and then the solid line it represents the theoretical, which is based on this equation. And then as you can see, the result is matched only in the region in the upstream region, which is around 30 degree, okay, which is in front of the circular cylinder. Okay, so this discrepancy between experimental and theoretical is known due to the viscous boundary layer that develops on the cylinder. Okay, so the main flow separates from the surface on the cylinder, so the main flow begin to separate, leading to the large difference between the theoretical frictionless fluid solution and the experimental results on the downstream side of the cylinder. Okay, so this difference basically due to the common type of fluid where where the viscous within near to the wall. Okay, and then not only the viscous, also the large pressure difference between stagnation point, which is upstream, and then low pressure region that develop a separation region and around the wake, and also the wake region. Okay, so you can see this video in order to understand why we just obtain the good agreement in the upstream of this circular cylinder. So as you can see, the flow separation beginning from this point, maybe around 30 degree of this circular cylinder, and then the flow starts to separate, and then this is a large wake region behind the circular cylinder. So that's why the velocity potential theory cannot be used if we want to if the fluid is considered a viscous fluid. Okay, so when we obtain the pressure difference, or we obtain the pressure, we can also obtain the resultant force. Basically, for the resultant force, or the force over the on the surface or on the body, we are interested to determine the drag force and also the lift force. Okay, so the resultant force per unit length developed on the cylinder can be determined by integrating the pressure over the surface. Okay, so the pressure is from the Bernoulli equation, and then Fx is force in x direction, which is parallel to the uniform velocity, and then this force is known as a drag force. So in order to get this force, it is integration between 0 to 2 pi, which along the surface, ps cos theta, a is the radius, and then d theta. Okay, so ps, as I mentioned before, this ps can be obtained from the previous slide, where it is obtained from the Bernoulli equation. Okay, so the same goes for fy, negative integration between 0 to 2 pi, ps sin theta a d theta. So fy is the perpendicular force between with respect to the uniform velocity or upstream velocity. So Fy is basically the lift force. Okay, so after substitute the Ps, and then we obtain that Fx equal to 0 and Fy equal to 0. So basically we can conclude that the potential flow theory incorrectly predicts the drag on a cylinder where it is obtained the result is 0. However, we know from the experience that there is significant drag developed on a cylinder when it placed in a moving fluid. Okay, so as you can see in previous video, there are flow separation. Okay, there are flow separation, and then there are weak region. There are large pressure difference between upstream and downstream or rear part of the body. So by definition, theoretically and practically, there are much drag developed around this shape. So basically this discrepancy is known as the D'Alembert paradox. Okay, so these two animation basically to show force over body and difference between potential flow theory simulation and viscous simulation, so that by watching this video you can get an idea what I explain, what the lecture is about today. Okay, so when a ping pong, so basically this is a ping pong ball is placed in a jet. So this is jet of air. The pressure different across the ball suspend the ball in the jet. Okay, so it is submerged around this jet. So this result is intuitively obvious. So however, the fact that the ball does not fall out of the jet, does not fall out of the jet, is not so obvious. Even though the flow are not exactly the same, the properties of cylinder or sphere in a uniform flow can be used to explain this behavior. Okay, so the jet impact the bottom of the ping pong ball and create a stagnation point with high pressure. So stagnation point in this bottom of the ping pong. The separated flow about the ball create a pressure behind the ball that is lower than stagnation pressure. So the vertical pressure imbalance produce a net upwards force on the ping pong ball that counteracts the weight of the ball. If the flow about the ball were inviscid and then uniform, then the pressure on the front and back of the ball would be the same and there would be no drag force to suspend the ball. So maybe you are asking, why does the ball stay in the jet? It is not moving out of the jet. Okay, so suppose that the ball move far enough to the outside. There are small part of the ball stick out of the jet. Outside of the jet, the flow is slowly moving and the pressure is large. So at the center of the jet, the flow speed is high and the pressure is low. Therefore, the ball experiences a net pressure force directed from the outside of the jet towards the center line that push the ball towards the center of the jet. Okay, so let's watch again. This video explain about what we call a real simulation based on viscous simulation and potential flow theory for the bottom video. Okay, so the use of potential flow has limitation for certain types and region of flow. For example, Potential flow cannot predict flow separation, as I repeatedly mentioned about this flow separation. So the two videos shows Streamline pass the same Streamline automobile. The video on the top shows Streamline for viscous flow past the car from a wind tunnel test, while the video on the bottom is from a house short shell, which mimics the potential flow streamline theory. Clearly, the potential flow provides a reasonable approximation for the flow on the front part of the body, but completely missing the flow separation and unsteady turbulent wake region downstream of the car. So as you can see, the flow separation and then unsteady turbulent wake behind the car, but for the potential flow theory, this is not captured. Okay. So okay, that's all.